And epsilon t is the white noise, as we said, with mean 0 and variance sigma squared. Without any derivation, I'm just giving you the properties of such models. So no matter what p is, mean of such variable of such series is constant, and it depends on these coefficients. So phi 0 divided by 1 minus phi 1 minus phi 2 minus blah 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 phi p. So if you have like AR2 model, so expected value is going to be phi 0 over 1 minus phi 1 phi 2. If you have AR3 model, phi 0 over 1 minus phi 1 phi 2 phi 3, and so on. So another important thing that we want to know is autocorrelation function. We discussed last time that autocorrelation function is unique for any linear time series models. So for AR1, autocorrelation function is unique. For AR2 is unique, and so on. So with the help of autocorrelation function, you can recognize what kind of model you are working with. So therefore, we want to know what is the form of autocorrelation function. And this is simple, very simple. You can see the similarity between autocorrelation function and the series itself. So correlation at lag age. So again, what is age? Age is how far is the correlated variable from period t. So this is gonna be phi 1 times rho h minus 1. So autocorrelation of smaller lag, autocorrelation of even smaller lag, and so on up to p. So p is the number of lags in the model here. So for example, if you want to find, and of course, so h must be larger than p. So when h equals to p, so the autocorrelation is going to be kind of reversed. For example, if p is 1, then there is going to be rho h equals phi 1 rho h minus 1. That's all. And if you are gonna find, I don't know, the autocorrelation of order 2, this is going to be autocorrelation of order 1, autocorrelation of order 0, and so on. So up to 0th autocorrelation here. And also we want to know what is the condition of stationarity. So the time series is stationary. In the previous lecture, we spoke about AR1 stationarity property, right? And this was that phi 1 must be less than 1 in absolute value, if you remember. So now we have more than one coefficient, and that's why we need to solve the following equation: x to the power of p, phi 1 x to the power of p minus 1, phi 2 x to the power of p minus 2, blah blah blah. And then all the roots of this equation must be less than 1 in absolute value, in modulus. So this is important thing. This is how we can verify the stationarity of time series. Okay, so as I said, there are no derivations. This is mostly to understand some important properties of this general class of AR models. What is mean, how autocorrelation function looks like, and what is the condition of stationarity. Now, MAQ model, so moving average of qth order. It looks as YT, equals to some constant mu, and this mu is the expected value of yt, plus the sequence of white noises. White noise at period t plus theta 1 times white noise at period t minus 1 plus plus theta q, so white noise at period t minus q. Q periods before t. And all these epsilons are white noises with zero mean and constant variance. So what are the properties of MAQ model? So mean is simple. It is simply mu. That's all. Variance. Variance of white noise expands with the order of this model. So if this is MA1 model, so variance is going to be sigma squared times 1 plus theta 1 squared. If this is MAQ model, so you will have a lot of coefficients here. And of course, all these coefficients are gonna kind of blow up the variance. So the variance expands. Autocovariance. So this is not autocorrelation, this is autocovariance, but again, so we can capture some property of autocovariance here. So theta squared multiplied by the, look, what's going on here. So we take sigma squared, sorry, we take theta h, so theta at leg h. So from here. Then we take theta h minus 1 times theta 1. So kind of we are going in the direction of kind of closer together. So here theta h minus 2 theta 2. And so I guess you captured the logic, what's going on here and here. And then we keep doing this until we reach theta q times theta q minus h. So what is the most important? That autocovariance has finite number of lags. So autocovariance is gonna be positive or negative, but non-zero when h is smaller than q because of this. And autocovariance is gonna be zero when h is greater than q. So when h is greater than q, this is gonna be negative, but negative lag doesn't matter. That doesn't make any sense. So that's why any autocovariances after qth lag disappear. In contrast to AR model, because for AR model it is possible. AR model has kind of infinite autocorrelation. So this is kind of the most important distinction. For autoregressive models, for AR models, autocorrelation function is infinite. So autocorrelation, so like the variable today is correlated also with variables kind of far away back in time. For moving average process, the memory disappears after qth lag. So today's variable, the value of the variable today, does not depend on anything beyond qth observation, beyond qth period. So everything before qth period doesn't affect the current value of series. This is the most important thing for the future questions of modeling. Now, when we combine both models, we get ARMA PQ model. So this part is AR model, this part is MA model. So we combine and we get ARMA PQ model. Again, we have white noises, epsilons here. What are the properties? So from AR part, we have mean. So the mean of this series coincides with the mean of ARP model. The ACF coincides with the ACF of AR model, but only for H greater than Q. So only for those parts where autocorrelation does not exist for the MA part. And for H less than or equal to Q, so the correlation is complicated because there is a combination of two autocorrelations, combination of AR autocorrelation and combination of MA autocorrelation. So therefore, I decided not to put this into slides because the formulas are kind of nightmares. You just need to remember that after MA part, the autocorrelation looks like the autocorrelation of AR model. Before that, you may expect some strange structure in autocorrelation. And again, the stationarity depends on the roots of AR part. So basically, AR part introduces the larger number of limitations to this model. Okay, what you have to remember from the previous slides is the distinction between autocorrelation for AR model and MA model. So we will see some examples just in several minutes, but this is the most important thing for the future modeling. Now, we also spoke last time about partial autocorrelation. I briefly mentioned that partial autocorrelation is kind of non-linear function of autocorrelation. So let's try to understand now in more details what is exactly partial autocorrelation function. So it measures the strength of the correlation between values of yt and yt minus h after controlling for the values between them. As I explained you last time, so yt minus h influences yt minus h plus 1, so the next value. Yt minus h plus 1 influences yt minus h plus 2, and so on up to the current value of yt. But there are kind of two channels of this influence. One is the indirect influence, so yt minus h influences yt through all this chain of influences. And another way of this influence is through kind of direct influence. So yt minus h can directly influence yt. So now we are looking for this direct part of influence of yt. So this is the partial autocorrelation. So let's see the example, so how it looks like. So suppose we have AR1 model. So yt minus 1 influences yt with this strength. So now we have AR2 model. Yt minus 2 influences yt with this strength. But also we can kind of imagine that yt minus 2 influences yt through yt minus 1. So it is easy to see. Let's kind of, let me show you just as an example. To understand why we are bothering ourselves with this. This is phi. phi 0, 2 plus phi 0 y2 y t minus 1 plus phi 2 y t minus 2 plus epsilon t. So again, so here yt minus 2 affects yt with the strength of phi 2 and 2. So now, if you rewrite this, with respect to t minus 1, like this. And now we plug into the expression of yt. So what would happen? We kind of plug it here. Then we immediately see that yt is influenced directly and indirectly by yt minus 2. So because yt minus 2 appears also here, it's going to be something like this. Phi 0, 2 times 1 plus phi 1, 2. We open the brackets. Then there is going to be plus yt multiplied by the coefficients here. So what are going to be? These coefficients are this coefficient plus this coefficient squared. Right, and plus phi 1, 2, phi 2, 2, y t minus 3. Isn't it? So this part goes here, this part goes here, this part goes here. Now yt minus 2, perfect. And then we have also epsilon t. Sorry, this must be epsilon t minus 1, right? It's not epsilon t. So this times epsilon t minus 1 plus epsilon t. So now, what is the correlation? What is the correlation? So not partial autocorrelation, but the correlation between yt and yt minus 2, t minus 2. So this is simply this part. So this is the kind of, so this part, the coefficient captures the effect of yt minus 2, the direct effect yt minus 2. So this one is phi 2, 2. and indirect. So through yt minus 1. Effect of yt minus 2. And this indirect effect is this part, so pi 1, 2 squared. And exactly here we have this structure that I showed you. Here, look, the structure of autocorrelation. So phi 1 times autocorrelation of order 1, this one. Phi 2 times the autocorrelation of order 2, this one. And so on. So it expands recursively. So again, this part is going to be captured by autocorrelation function. But partial autocorrelation is just this part. So how the this part. So how the leg of variable, so second leg of variable, for example, affects the current variable after controlling for the effects of everything in between, after controlling for all these variables between them. So here, so basically what is partial autocorrelation function is just a sequence of these coefficients, phi 1, 1, phi 1, 2, 2, phi 3, 3, up to phi pp. So this is the partial autocorrelation function for a RP model. And we usually denote this with alpha h. So alpha 1 is going to be this coefficient, alpha 2 is this coefficient, alpha 3 is this coefficient, and so on. And what is important, that PACF, partial autocorrelation function, for ARP model cuts off at lag p. So after lag p, partial autocorrelation function does not exist. So it's 0. So in order to summarize, how can we identify what kind of model we are working with? So kind of when observing the models, when trying to make some identification. So MA model has the following property. MA model has ACF, which cuts off at lag q for MAQ series. So after lag q, ACF is 0. Doesn't exist. For AR model, partial autocorrelation cuts off at lag p. So with this knowledge, we have some tools to identify what kind of model we are working with. Because nobody says you, well, if you want to forecast the prices of Gazprom follow AR3 model. No, of course, nobody says you this. You need to identify which model is more appropriate for this. And this identification is made through these two functions, either ACF or PACF. So also we know that MA series are always stationary, and for AR series we also need to test for the unit root, for the characteristic roots, that they are less than 1 in absolute value. So now here are some illustrations of what we've been talking about. This is AR1 model, so 0.7 yt minus 1 plus epsilon t. This is ACF for this model, for 8 lags. You see that it slowly decays, but still kind of it goes to 0, but never approaches 0. It starts with 0.7. And here is a PACF. So partial autocorrelation has only one value at the lag 1 and then disappears. Everything is 0. Exactly what I was talking about when I said that for ARP model, PACF cuts off at the lag p. here. So now, this is AR2 model. For AR2 model, you see that the autocorrelation function, well, it kind of has these waves because we have negative value here, and because of this negative value, it kind of goes to negative and then positive and so on. So you also can see such waves, no problem. But partial autocorrelation has first and second legs, and that's it. Here are MA models. So this is MA1 model. And for MA1 model, we have one leg for autocorrelation function and everything else is zero. And you see that there is infinite stream of partial autocorrelations. Completely opposite to AR models. Here we have MA, no, this is ARMA 1.1 model, right? Because this is AR part, this is MA part. And for ARMA, you see that we have kind of these fluctuations there and back for ACF. And also we have the similar to MA model PACF. Well, this structure comes because of AR part. This structure comes because of MA part. So basically it must give you some ideas how to identify which type of model we are working with. If you see something like this, or this together with the kind of decay in ACF, this is AR model for sure. When you see something like this is a MA model for sure. When you see something like this, well, maybe you need to combine both AR and MA models in one model. Any questions, guys, regarding all these things? So we are talking about them in order to move to the practical part. So how to identify which model suits better for working with time series. Well, if there are no questions, then let's move to the core part of this lecture, Box-Jenkins methodology. So this is about how to work empirically with the real data and how to model time series kind of in the most appropriate way. So these two authors back in 1970s proposed the following algorithm for modeling time series. And this algorithm is still kind of the standard algorithm for doing this. So first of all, we need to identify what kind of model we are working with. And we've been talking about the ways of identification just recently. Then we need to select the appropriate model. Next, after selecting the model, we need to estimate parameters. So it must be familiar to you, like this sentence, parameter estimation. So we've been doing this for the whole last year in statistics and econometrics, and also like the whole semester we've been doing parameter estimation. Because parameters of the population model are not given to us, right? So we need to estimate them with the help of data. Then after any estimation goes statistical testing. So we need to test the significance of the computed coefficients. So basically these three steps must be done. Now, let's take a particular example, practical example of time series. GDP growth in Russia starting in 1990 to 2021. So we want to first inspect this plot in order to identify if there are some trends, breaks, or other signals of non-stationarity. So I would say, kind of like if we would practically work with this, that probably these series are not stationary, because they behave like we spoke last time, that stationary time series are fluctuating around some constant value. So we see that there is a long period of positive growth around 5 to 7%. Then, well, this probably is stationary, but kind of several years. Then we have this trending part from negative values to positive values. And then we have this part starting from 2010. So if we would inspect something after 2022, we would probably observe something else. So, but let's kind of, this is if we want to be very, very kind of formal and very correct. For now, let's kind of put it aside and let's assume that we are working with stationary series, because we know nothing about non-stationarity, we know nothing about all these breaks, trends, So we would come back in the next lecture, next Saturday, to this question. So we've planned to speak about non-stationarity issues. So let's now concentrate on this. So now, if we want to answer the question, so what kind of model is this? AR, MA, ARMA, AR1, AR2, MA1, MA2. What is the model appropriate for working with this time series? So this is the first important question. And if you want to understand the orders of P and Q, we have to estimate them from the data. And the most relevant statistics for this are sample ACF and sample PACF. So the distinction between sample ACF and just ACF is the same as the distinction between population parameters and estimators. So population parameters are constant, unknown, they are theoretically somehow established, and all these relevant things. Sample values are taken from samples, right? So sample ACF is going to be derived with the help of data. Sample PACF is going to be also derived from the data. And we need to take the last statistically significant lag for both. So statistically significant means that it significantly differs from zero. So this wording must be familiar to you. We've been doing statistical significance a lot of times. So this is the picture. This is autocorrelation plot, sample autocorrelation plot for the series of Russian GDP growth. Look, the area here, this blue area, shows the confidence interval. So the confidence interval for zero. If these points fall into the blue area, it means that this lag is not statistically significant. It does not differ from zero. So we have only two lags, here and here, that significantly differ from zero. Well, it suggests what? It suggests that probably our model is MA2 model, because we know that ACF cuts off at the lag Q for MA models. Again, we don't care about other points. Why? Because other points all belong to this shaded area, and shaded area is the area when we cannot, so the data does not comply with the alternative hypothesis that the lag is non-zero. So now, what is about partial autocorrelation? It looks like this. And again, we are in a strange situation, because partial autocorrelation cuts off at 1, and probably this is AR1 model. But it happens in reality. It happens that not every time series, like practical, empirical data, would unambiguously suggest you that, well, this is unambiguously MA or this is unambiguously AR. No, sometimes you would see something like this. And well, we need to choose between two. We need to choose which one suits us better, either MA model or AR model. So for practical applications, AR is better because AR is understandable and easier to estimate. But we can estimate both. So you will go through the code, through the Python code, how to build these pictures on the exercise session. So there is no clear signal about the model type. So let's so what is this? What this table shows us? Well, basically, these are the estimated values of ACF. Here, the first column. So these points 1, 0, 6, 0, 5, and so on here. These are the confidence intervals, the borders of the confidence interval, lower border and upper border. You see that 0 does not belong to this, 0 does not belong to this. But then every other interval includes 0. And you know, if 0 is inside the confidence interval, then we cannot reject the hypothesis that the parameter is 0. Therefore, we concentrate on two legs for ACF model. Now, regarding PACF. For PACF, this fourth column is the estimate of PACF values here. And these are the borders of the confidence intervals. So lower and upper border. So we see that only the first leg, confidence interval, does not include 0. All the other confidence intervals include zeros, so that's why they are not statistically significant, and we cannot believe that, well, that the legs are non-zero. Now, going to the estimation of parameters, the second part of Box-Jenkins methodology. So if we consider that we are working with AR model, AR1 model, for example, we can estimate the parameters with the help of OLS. This is simple, and basically there are relatively weak assumptions that OLS estimates are consistent, asymptotically normal. So all the assumptions that we've been working with in cross-sectional econometrics, they work also here. So we can use t-statistics to investigate the significance of coefficients, and everything works well in this case. So that's another reason why AR model is more popular in the case of time series, if you have a choice, of course. For MAQ, it is more problematic. It is more problematic because we don't know the error terms. We don't know the white noises. And we don't know their series. So that's why we either estimate them with maximum likelihood methods or with iterative least squares methods. So we are not gonna talk about them in details, don't worry. Yeah, the problem is that lagged white noises are unobserved, and we need to estimate also them together with the parameters. So the estimation process takes more resources. So our example, we have two candidate models, a R1 model, a MA2 model. So now this is the output from Python. So no need to do this in details. I mean, with a kind of with pen and paper methods. So we know how to work with technology. So this is the estimation parameters, constant, mu, theta1 estimate, theta2 estimate. What is interesting that theta2 estimate is not statistically significant. So we can probably reject the version that this is MA2 model in the favor of MA1 model. But for now, we have something like this. So this is the MA2 model for Russian GDP growth in 1990 to 2021. Here are the results for AR1 model. So constant, well, it's not significant. This is the lag for, this is the coefficient for the first lag, and this is the estimate for sigma squared for the variance of the error term. So here, the result. Well, we have two models. For now, we don't know which one to use. As I said, practically AR model is more appropriate. So that's why we would work with this, probably. So we'll see. But so I demonstrated you basically how to estimate both. As for the practical steps, how to get this output with Python, you will do everything on the exercise session. So don't worry. Now, next important thing. We need to verify that with the help of models, we absorbed all structure of this series, everything that we know about the series. So any model includes white noise as a component, includes these errors. And we need to promote we need to perform the model diagnostics. Starting with examining these residuals, they must pass all tests that they are white noises. This is important. If you see that the series of residuals still have some residuals, some still have some autocorrelation structure, we should go back and correct our initial model, because not everything has been captured in the model. So we have to test whether the autocovariances or autocorrelations of residuals are zero. If the model fails to pass the test, we need to modify the model. How do we test the residual autocorrelation? So first of all, we need to look at the ACF of the residuals. And we need to see that all lags are not significant. So we can test the joint significance with the help of so-called Ljungbox statistic. So I'm not going into details how the statistic is computed, but this is one of the statistics, one of many statistics that we have been talking about around the last year. So we know there are chi-square statistics, F statistics, blah, 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 a lot of other statistics. So another type of statistics is Ljungbox statistic. And sometimes we can test ARP model against ARP plus R model or ARMA PR model. And so just adding several legs here. And after adding several legs here, we can, well, decide whether there is some residual autocorrelation or not. Say bless you to my dog. That was the noise from him. So this is the autocorrelation plot for the residuals coming from a MA2 model. So we see that no lags are significant. So basically everything is fine. So this is partial autocorrelation for the residuals from MA. So there are some strange points here, but well, we can probably forget about them. But still, they must somehow draw our attention. But everything before is 0. Yeah, we can take it as no residual autocorrelation in MA2 model. So now regarding the residual autocorrelation for AR1 model. So nothing here. And again, almost nothing here except for the 2 past lags. Well, that's fine. So now, this is the output from Python when we test for the residual autocorrelation with the help of 2 statistics. So basically not one, not only Ljungwalk statistics, but also Breusch-Pagan statistic. So another statistic that tests whether there is some residual autocorrelation or not. So we can concentrate on p-values here and here. These are the lags from 1 to 10. So if you see, as usual, if p statistic is less than 5%, then the null hypothesis is rejected. What is the null hypothesis here? The null hypothesis here, there is no autocorrelation between current value and lag 1 value, current value and lag 2 value, and so on. So we see there is no residual autocorrelation here at any lag with the Ljungwalk statistic. There is no residual autocorrelation here with the Breusch-Pagan statistic. Well, basically, it means that everything is fine, and for MA2 model, there is no residual autocorrelation. So the same table for the residuals coming from well, definitely from AR1 model. No, this is a typo, not MA2 but AR1 model. So the same thing we can see. P-values here are large, p-values here are large. So well, basically there is no residual autocorrelation for AR1 model as well. And we passed these tests. So for the future, we can work with MA2 model or AR1 model as the appropriate model for forecasting a series of Russian GDP growth. This is our kind of practical conclusion. So the model suits unless we find some other specific things that we have not been discussing yet. To conclude this topic, what do we know? ACF and PACF are able to uniquely characterize the linear time series models. When we model time series, we start, so our first step is to build sample ACF and PACF. So this is the first necessary step. Then we choose the appropriate candidate models based on these 2 objects, remembering that either ACF cuts off for MA model or PACF cuts off for AR model. Sometimes we are indecisive which model is better because both objects can send you kind of contradictory signals. So then we need to perform the diagnostic tests over the models in order to verify that residuals do not have some leftover correlation there. So that's all about practical steps in modeling time series, like kind of like the most general view of working with this. Now, to conclude this part, there is again quiz. that is going to be available from November 19th to November 24th for this topic. Another quiz based on this lecture. And don't forget about the home assignment. The home assignment from the past that has been extended. Questions? Well, don't forget that we have the next lecture. So please, let's start at 15:15, if you don't mind, kind of in 20 minutes.